All right, so I started the recording. All right, so we're going to spend a few minutes. We're going to talk about Grignard reagents and how to use Grignard reagents in the presence of alcohols. And so one of the things that I want to get into is the protecting groups of alcohols. And talk about, and so there's two reactions that you have to know, and that's the reaction to protect alcohols and the reaction to deprotect them. So remember what I was saying about alcohols being incompatible with carboxylic acids because they'll deprotonate that OH group and that'll go on and do some chemistry you're not interested in. Well, the same thing is true with alcohols. If you have a reagent that has an alcohol on it and you want to create additional carbon-carbon bonds, then one good option for that is the Grignard reagent. But if it has alcohols on it already, you're not going to be able to do that reaction without first protecting the OH group. And what we mean by protecting is we're just actually going to do a reaction that turns it away, that stops it, takes it from an alcohol, turns it into some other functional group. In this case, it's going to be an an ether. And then we're going to, once we do the Grignard reaction at that point, then we're going to deprotect it and turn it back into an alcohol. All right. Okay, so let me jump in and start my screen again. And let me write down what I'm talking about. If I have a compound that has an alcohol on it, and say I want to do something like 1, 2, 3, 4 carbons, 1, 2, 3, 4, 5, 6 carbons. And let's say I want to add 6 carbons to it, or add 2 carbons to it. And form this structure. Well, in order to do that, I have some work to do. And so I want to talk about the things that I have to do in order to make that happen. I can say, what I'm going to tell you is that I can use a Grignard reagent. And if I go, and remember, when we're doing synthesis, we want to count carbons. I like to tell all my students, if you're not counting carbons, you're not doing this right. And so this structure that's the product has 1, 2, 3, 4, 5, 6 carbons. The structure that's the reactant has 1, 2, 3, 4 carbons. And so at some point, we're going to need to add 2 carbons. I can say, look, I can do that with a Grignard reagent, or I can do that with alkylation. And let's forget about alkylation for now. I'm sure you could accomplish the transformation with alkylation, but I want to talk about it for Grignard's sake. And so here's the reactions that I want you to write down. And unfortunately, I don't have a separate reaction board. So I don't know what I'm going to do to signify here's a reaction that you have to know, other than to say, here's a reaction that you have to know. If you react an alcohol group with TsCl in the presence of triethylamine, then you will turn the alcohol into this guy. Okay. This structure, OTMS, this is not reactive towards Grignard reagent. And so this is what's protecting the alcohol. Then to deprotect it, if you react this thing with TBAF, and I think it can also be HF, I think it could be HF as well. We're going to go with it for now. Yeah, or fluoride minus. And so you can then turn this thing back into the alcohol. And so this is the protection step. This is the deprotection. And so because Sumaya asked me about it earlier, and I know she loves retrosynthesis, let's see if I can get some room here. Let's approach this problem from a retrosynthetic perspective. Well, I know that I had to do a deprotection. So I know that TBAF was probably my last step. And the original alcohol was what was deprotected. So then what does that imply about this alcohol? That must have been the alcohol that was formed from the Grignard reagent. And so now I can think about, well, then what would it have looked like, and what would the Grignard reagent have been? Well, I've already established that I have to add 2 carbons. So perhaps it was a 2-carbon Grignard reagent in the presence of water. Now, the next thing we have to do is we have to think about what are the functional groups that Grignard reacts with. Well, Grignard reacts with carbonyl group. And so where was the carbonyl? The carbonyl was in the location where the OH is. And so if I keep going backwards, and I need to give myself some room. And so I'm going to just kind of walk back it just a little bit. I've still got OTMS. And now I've got my 1, 2, 3, 4 carbons. And at that point, there was a carbonyl group. And so at this point, I want to bring in a lot of the reactions that we reviewed today. And so this is a little bit of a complicated retrosynthesis. I made it complicated on purpose because I wanted to kind of get back at some of those things that we were talking about. And so now I want to stop talking about Grignard. I'm going to stop talking about the alcohol chapter, and I want to remind you about some of the stuff from alkynes and some of the stuff from alkenes. And so I want to ultimately form this carbonyl group at the end of the molecule that I start with, and I need that carbonyl group to, because it's in the end position, one might be able to say this is in the anti-Markovnikov position. So I need to form an anti-Markovnikov carbonyl group. And if I remember how to do that, if I have a alkyne, 1, 2, 3, 4, and there's my OTMS, and I react that alkyne with R2BH, H2O2, and sodium peroxide, it will form an anti-Markovnikov alcohol, which would be an enol, but the enol tautomerizes into an aldehyde. And so this is a functional way to make the carbonyl group. All right, so I want to, this is an example of retrosynthesis, and I know I'm slowed it down just a little bit, but I am still kind of going fast. I get that. If you don't know all of the reactions that I'm talking about by heart, don't worry. You know, you have some time to review, but I'm just kind of giving you an illustration of how these things relate to each other. In order to form the alkyne, I don't want to use alkylation, not because of the fact that I told you forget about alkylation, but because at this point I've already got all the carbons that I need. So I don't want to change the number of carbons. So what does that mean? That means I needed to do an elimination reaction where I eliminated, there's 1, 2, 3, 4. There's my O, TMS. And what do you eliminate? You eliminate a dihalide. And you do that with sodium amide. And I know this is small. Let me just back that up. I'll write it in another location. Sodium amide and water because it's terminal. Okay, well, how did I make sodium amide? Well, it must have been from, or how did I make the dihalogen? Well, it must have been the addition of X2 in this case. And then this is, now I'm all the way back to my very first protection step, TsCl and triethylamine. And so let me get back to sort of a summary of what we just did. The main thing that I wanted to point out in this particular example is that alcohol is incompatible with Grignard. In order to use a group, a functional group that, or a molecule that already has an alcohol group in a subsequent Grignard reaction, I have to first protect it and then deprotect it in this series of reactions below the red line. We were given a synthesis problem such that I wanted to transform A into B. And so I had to think about how I accomplish that synthesis, how I accomplish that transformation. Well, because I'm couching it in terms of protection and deprotection, it was obvious to us that we had to protect this alcohol and then later deprotect it. And so that's going to be it. Even though we were thinking about it retrosynthetically, we knew that that was the first step and that was the last step. Then I took a diversion into Orgo 1 and I brought in some of the reactions of alkynes, some of the reactions of alkenes, and of course I brought in the basic Grignard reagent reaction in order to form carbon-carbon bonds from carbonyl groups. We put all of these things together, and so how many steps was it total? 1, 2, 3, 4, 5, 6, 7, 8, 9. It was a 9-step synthesis, and you know, to be honest, that's probably about as challenging as it's going to get. And so what I want to do is I want to just pause just for a beat and see if you guys have any questions. I'll let you write them in chat. All right. So let's move on then. Let's continue to talk about other reactions of alcohols. And so we want to kind of leave the realm of Grignard reagent, and we want to talk about other reactions of alcohols. One thing I can, and these are essentially substitution reactions. And so one thing I can do is I can take an alcohol, I can substitute it with a chlorine in the presence of zinc chloride. I can also perform the same reaction, or at least accomplish the same reaction in the presence of SOCl2 and pyridine. So Tierra asked the question, is working backwards the best method for alcohols in general as far as synthesis? Remember what we say about synthesis, and this is what Sumaya pointed out earlier. We talk about it in terms of being retrosynthetic analysis. And the reason we say retrosynthetic analysis is because we do work backwards. Now, what does that mean? Does that mean, does the protection step have to be first? No, it could have been one of the other steps in the middle, but it had to be definitely before the Grignard reaction. And so to go back to the other question, is it the best method? The answer is maybe, probably, yes, no, I don't know. I suggest you try it that way. Personally, my experience was I resisted it, and I wanted to know the reactions and go and just do it forward, just do the solution. But what I realized is that until I actually knew every single reaction really, really well, like at the 98, 99 percentile, I couldn't successfully do every synthesis problem in the forward direction. When you do a synthesis problem in the backward direction, what it does is it gives you it helps you organize your thoughts. And so I do recognize that it's a difficult way to approach problem solving, but it is the method that we've been doing this for. We've been doing this with since the beginning of time, and so it does have its benefits. Do you have to do it? You don't have to do it. I'm sorry if that doesn't answer your entire question there, Tiara. Okay. I can react an alcohol with PBr3 and do the same type of substitution. Instead of a chlorine, I can do it with Br. It's like a benzene ring, but with one of the CHs replaced with a nitrogen. Yes, that's what pyridine is. Correct. Correct. Good. Thanks. I'm glad to hear that. All right. And so I guess here's what I want to do in the limited amount of time that we have left. I'm going to actually leave it there and say, here are 3 reactions. And these are the 3 substitution reactions that I've introduced after the protection reactions. What we're going to do is we're going to come back in our next class, and we're going to do a mechanism for the addition of SOCl2. And then we're going to move on from there. But what I'm going to do is I'm going to stop the recording.